Okay, hi guys. This is a supplementary class because we have back-to-back holidays on Monday. I want to talk about interrupt. How interrupt is processed or how exception is processed in computer system. Because we are talking about what this precise interrupt support in out of order processor, right? The thing I want to explain is this. All instructions before interrupted instruction must be completed, right? And the instructions following interrupted instruction must not change architectural state. Okay, that is the one, right? So, to explain this, probably I need to explain interrupt and exception first, right? I'm using PowerPoint from this lecture, COSE 321. So if you go back to my class page, check out this. COSE 321, Computer System Design. Right? ID, COSE 321. Password, same password, lowercase ESCA. So go into the page, then scroll it down. There's an interrupt lecture slide, okay? And also this one, exception related PowerPoint, page 4, and here limits. So interrupt. Okay, there are two, super important events happening inside the computer. These two are called, the first one is called interrupt. And second one is called exception. Okay. And interrupts are typically generated from IO devices. For example, if you, move your keyboard, right, this mouse, right, then interrupt is generated. If you press your keyboard, interrupt is generated. If I press this, spotlight, look at this. Interrupt is generated, and interrupt service routine is executed and moving this mouse, right? So that is the one. And exceptions. Exceptions are typically generated while executing your program. Okay. So exceptions are generated internally inside the CPU, right, while executing your program. And from the sense, interrupts are generated from the outside of the processor, because those are typically generated from IO devices, right? And these two terminologies are, used in a very mixed way. Some people say, so combining these two, some people say just interrupt, and some people say just exception. But I want to differentiate these two, right? And this PowerPoint is based on ARM architecture. And ARM architecture, as you can see here, right? Exception vector table in ARM. Exception vector table, they are combining these two and place these different sources in one, table. For example, interrupt here too, and supervisor call is also interrupt. And undefined instruction, that is exception, and prefetch data abort. These two are exceptions. So they put exception interrupt in one table. So you have to look up that table before jumping into interrupt service routine. So again, these two terminologies are used in a very mixed way sometimes, right? And the mechanism to handle this interrupt exception is very specific to CPU. meaning, x86 has its own mechanism to handle, these two. And ARM, this CPU, has its own way of, processing interrupt. And RISC-V has its own way, its own protocol, in other words, right? So you need to study CPU architecture, okay, separately. But the good news is, high level operation of handling interrupt or exception is super similar, very similar. So once you understand one architecture, processing interrupt, very straightforward to understand the other two, the other CPUs. So let's talk about interrupt, right? And how interrupt is handled in ARM. Interrupt, right? Interrupts are typically generated again from I/O devices. That is called hardware interrupt. But sometimes interrupt is generated internally while executing your program. Okay, so every CPU is providing very special instruction called software interrupt instruction. In ARM case, supervisor call instruction. So in ARM case, if you put SVC instruction, for example, sharp 1, so that is instruction. Then CPU execute this code, then software interrupt is generated in ARM case. x86, int, that is instruction. So if you put some code like this, then CPU execute this one, then software interrupt is generated. But here, let's focus on hardware interrupt. Hardware interrupt. How hardware interrupt is handled in CPU. First, big picture, right? So here, take a look at the first lecture slide. Computer system, right? Computer system is composed of 3 big components: CPU, memory, and I/O devices, right? The super simplified block diagram. You have CPU and memory connected through, this data and address bus, right? So you have your program. Your program is placed in memory, and a CPU has very special register called program counter, right? So program counter is pointing the location 0, where the instruction is placed. So that instruction is coming in inside the CPU executes it. And program counter is automatically incremented by 4. That is applied to CPU, memory. And then instruction at that location is coming in, CPU executed, right? So CPU is doing that operation forever, okay, until you turn off the computer, right? Then the question is, you have many different I/O devices in your computer, right? And these I/O devices are mostly running autonomously, right? But sometimes it requires attention from CPU. Some event generated, right? You move your mouse, right? You press your keyboard, then you need attention from CPU. The question is how that event is delivered to CPU. So for that purpose, at least every CPU is providing at least one input connection. That is called interrupt, input connection, right? So somehow, let me show you this PowerPoint. This one is better. Same block diagram, right? CPU, memory connected, the many different I/O devices. So every I/O device device has one output connection, generating some event, and those events should be somehow delivered to CPU, okay, through that connection. So how would you connect these, outputs from I/O to this one input? Probably one obvious, connection is using just simple OR gate and connect each output to this OR gate input, right? Like this. That means any of the input is asserted to 1, then OR gate, right? So it is aggregating. So any of the input is 1, then output is 1. So CPU then recognize that event, okay? So for example, okay, you have that connection, right? That connection got asserted from 0 to 1. So OR gate, right? So 0 to 1. So that information is delivered to CPU. So you have, clock input in CPU, right? So let's call this interrupt. So clock is running like this. Okay, this is clock. Then this input is asserted like this. So every rising edge of the clock, CPU can check out that input connection. So at this time, probably 0. So at this time, 0, no event. But at this time, right, the event happened, right? At this time, event happened. So CPU, recognize that event and then, stops what it is executing, then jump to interrupt service routine, right? So interrupt. But this simple OR connection is not that, efficient. Why is that? Because, assuming that there are many, not 5, many IO devices, say you have 100 different IO devices, and one guy generated the interrupt. Then the question is, how do you know who, generated the interrupt if you have simple OR connection? So then the solution is using a software. You have to poke around every IO device, okay, saying, okay, you generated the interrupt, or you generated the interrupt. You have to poke around, every IO device, right? So it takes a lot of time to figure out the interrupt source, right? So that is a very, interrupt latency. Interrupt latency is going to be very long. Okay, that is one problem. Second problem is, what if, multiple devices are generating event at the same time? Who do you want to service first? So some priority mechanism should be implemented, right? So for that purpose, we have a very special hardware component called the interrupt controller. Okay, so every computer system has interrupt controller implemented inside the computer system. Okay, so there are many different, not many, but several different names for this. APIC or PIC. APIC is what? Advanced Programmable Interrupt Controller. PIC. So without advanced, right? And some hardware module is called INTC. In ARM, they call that module as GIC, Generic Interrupt Controller, right? So whatever the name is, the function of interrupt controller is very similar. So it is aggregating interrupts from many different sources, then forward that interrupt to CPU. But it is implementing some intelligence like priority registers. So using priority registers, you can set the priority. For example, timer priority number 10, UART priority number 9, okay, and so on, right? So when multiple devices generate interrupt, so interrupt controller knows the who has the highest priority. So then you can forward that interrupt to your CPU. Okay, that is the one. An important thing for this class is how interrupt is processed, right? So this is the one. So again, this one is specific to ARM CPU, but the high level, the mechanism of handling interrupt is the same essentially. So once you understand this is interrupt handling in ARM, then the same thing will be applied to x86 architecture. Okay, so here we are assuming while CPU is executing some program, some main routine, interrupt or exception is generated here. Then the goal, what is that? The goal is there is an interrupt service routine. Assume that the interrupt got generated from interrupt is generated from keyboard, right? Then this service routine is keyboard the handling, the interrupt service handling routine, right? So what you have to do is you have to jump to that handler. Then after processing this interrupt, the code, then you are supposed to come back, right? That is the big picture, right? So some more detail. So this one is the full, the picture, full the mechanism of handling interrupt in ARM processor. There is an interrupt, vector table. Okay, interrupt vector table, and depending on the interrupt source or exception source, right? So you will look up this table, then jump to appropriate interrupt handler routine. So again, every CPU, right? Every CPU is defining its own, not the CPU vendor, x86, ARM, RISC-V, they define their own vector table. So this one is specific to ARM. Okay, so interrupt got generated, for example. Okay, then CPU should execute the branch IRQ ISR. So branch instruction. So branch to here, then interrupt processing, then you have to come back. That is the execution flow, right? The important thing you have to remember is this is a typical interrupt handling routine. So before the main handling routine, you have to push CPU context to the stack. Meaning you have to back up architectural registers to the stack. Okay, so why is that? In ARM, we have only 32-bit. 32-bit ARM CPU. We have only 16 architectural registers. Okay, and for simplicity, okay, those registers should be backed up to the stack. Stack is what? Stack is simply memory area you reserve for backing up those registers. And sometimes you have to restore, right? Backup and restore. Backup restore operation, right? Sometimes you backup because you have a limited, very small number of registers. Sometimes you backup, then you are free to use those registers, right? So push, backup means push operation, right? And restore means pop operation. Right? So you have to push CPU context architectural registers to the stack. then you are free to use architectural registers in ISR, the main body of ISR, right? Then after you are done processing interrupt, then you have to restore that interrupt, okay? The CPU context, right? So that is typical and almost a standard procedure of handling interrupt, okay? You refer to vector table. So depending on the kind of interrupt, you select one guy. So in case of interrupt, this entry 0x18 or 0x1c in ARM case. Page fault happens or TLB miss happens. You have to execute the code in a 1-0 location. Okay, that is the protocol, right? So promise between CPU hardware and software, the programmer. Okay, so that is the one. So going back to, so the same, same mechanism, handling mechanism applies to exception handling. Okay, so going back to this, our dynamic scheduling PowerPoint. So interrupt got generated, right? So let me draw pipeline. Let's say you have a memory access instruction, LW instruction, okay, R3, then 4, R4. So I'm writing, some example code, right? R2, R3, R4, okay, and subtraction, R5, R3, R2, okay, anything is okay. So if you draw a pipeline execution diagram, instruction patch, decoding, execution, memory access, write back. Okay, assuming simple, 5-stage pipeline, patch, decoding, execution, memory access, write back. So clock is running like this. Okay, patch, decoding, execution, write back. Then assume that interrupt got generated here like this. Interrupt. Okay, we have CPU interrupt input. So you move your mouse, right? So at this time, then what should happen is CPU complete that instruction, finishes that instruction, right, to the end. Then even though those two instructions are in the pipe, right, CPU will flush out these two instructions. Okay, then jump to interrupt service routine. But before you jump to interrupt service routine, you refer to that vector table, right? Vector table first, then interrupt service routine. So anyway, what happens is from execution, right? Then you are patching new instruction from ISR or vector table, right? Patch, decoding, execution. So assume this one is from interrupt service routine. Okay, you executing interrupt service routine. So after you are done processing this code, then you are supposed to come back. Suppose come back this point, right? So the PowerPoint says, okay, so all the instructions before this interrupted instruction must be completed, but the instructions following following this interrupted instruction should not change architectural state, because you are going to come back to this point, right? Then execute from there. We will talk in detail about this, how that is implemented, in out of order CPU using a reorder buffer. Okay, but this supplementary class, I like you to understand. I like you to know the basic mechanism, okay, of handling interrupt in CPU. Okay, that is everything. But again, check out this class page and PowerPoint. Okay, interrupt and exception. Interrupt, exception, but this one is focusing on TLB. Okay, TLB and page fault. Okay, that is it. I'll see you in the class.